It's mysterious and wondrous. Welcome to the world of relativity. The conservation of energy, the relationship between energy and mass, and the relationship between energy and momentum are all important topics in special relativity. In this video, we will introduce these energy-related concepts. Just like momentum, in Lagrangian mechanics, the energy of a system is defined as a function of the Lagrangian and generalized coordinates. In this definition, P represents the generalized momentum, Q represents the generalized coordinate, and Q dot is the time derivative of the generalized coordinate, also known as the generalized velocity. By summing the product of the corresponding generalized velocity and generalized momentum, and then subtracting the Lagrangian, we obtain the system's energy. We use the letter h for this quantity because it is known as the Hamiltonian, which plays a crucial role in Hamiltonian mechanics. The Hamiltonian represents the total energy of the system. Let's first examine the consistency of this energy definition with the energy definition in pre-relativistic classical mechanics. By replacing the generalized momentum with momentum mv and the generalized velocity with velocity v, this sum essentially becomes twice the total kinetic energy. The Lagrangian is the kinetic energy minus the potential energy. From this, we can calculate that the total energy of the system is the sum of kinetic and potential energy. Thus, the energy definition in Lagrangian mechanics is consistent with that in classical mechanics. Energy conservation can be directly derived from the definition of energy. Energy conservation means that the system's energy does not change over time, i.e., the derivative of energy with respect to time is zero. Let's derive this. Before the derivation, let's list two equations. P equals the partial derivative of L with respect to Q dot, which is the definition of generalized momentum. P dot equals the partial derivative of L with respect to Q, which is the Euler-Lagrange equation. Substitute the definition of energy. Apply the product rule for derivatives to expand the first term. Use the chain rule for derivatives to expand the second term. Substitute the two equations listed earlier and simplify the terms. The derivative of energy with respect to time equals the negative partial derivative of the Lagrangian with respect to time. In other words, as long as the Lagrangian does not explicitly depend on time, the system's energy is conserved. It's important to note that in principle, the Lagrangian can include time as a variable in addition to the generalized coordinates q and generalized velocities q dot. The zero partial derivative of the Lagrangian with respect to time means that the Lagrangian is expressed only as a function of q and q dot, without time t as an explicit variable. This does not mean the Lagrangian does not change with time, as q and q dot themselves change over time. This is the definition of energy and energy conservation in Lagrangian mechanics. Once the Lagrangian of the system is determined, the energy can be calculated using the formula, and as long as the Lagrangian function does not explicitly depend on time, the system's energy is conserved. Once we know the Lagrangian of a system, we can calculate the system's energy using a fixed formula. By defining the generalized coordinates in the energy formula as the position coordinates of a particle in the Cartesian coordinate system, the corresponding momentum becomes the momentum in the three spatial directions. In previous videos, we introduced the Lagrangian and momentum for a free particle not subjected to external forces, substituting the relevant values and expressing the time derivatives of spatial coordinates as velocities in the corresponding directions. With some simple derivations, we arrive at the energy formula for a free particle in relativity. This formula is derived in a unit system where the speed of light is set to 1. In this unit system, energy and mass share the same units. If we keep the speed of light c, the energy formula for a free particle needs some adjustments. Let's explore the relationship between the energy and velocity of a free particle using a graph. In Cartesian coordinates, plot the relationship between velocity and energy. As the absolute value of velocity increases, the particle's energy also increases, consistent with our general experience. When the absolute value of velocity approaches the speed of light, the particle's energy tends towards infinity. This indicates that any particle with mass cannot reach or exceed the speed of light, as it would require infinite energy. Moreover, we can see that even when the particle's velocity is zero, it still has energy equal to m times c squared. This is the famous mass energy formula. This energy is called the rest energy, which is the intrinsic energy of the particle. Additionally, we see that when the velocity is much less than the speed of light, the particle's energy can be approximated by its rest energy plus the kinetic energy from Newtonian mechanics, which is 1/2 mv squared. This shows that the energy of a particle in relativity differs from that in Newtonian mechanics in two ways. One part is the rest energy, which Newtonian mechanics does not account for at all. The other difference is that in relativity, energy increases more rapidly with velocity compared to Newtonian mechanics, especially as the velocity nears the speed of light. This is the energy of a free particle in relativity. It depends on the particle's mass and velocity, but it significantly differs from the energy in Newtonian mechanics. In previous videos, we introduced the concept of four velocity. It's a four vector, and you can calculate four velocity using conventional velocity. We also derived the formulas for energy and momentum in relativity. Now express them in vector form. It becomes clear that the energy-momentum vector is essentially the mass multiplied by the four velocity. Since mass is a constant, multiplying a four vector by a constant still gives a four vector. Therefore, the energy-momentum vector is also a four vector. We typically refer to this four vector as the four momentum, even though its time component is energy. We've also mentioned before that the difference between the squares of the time and spatial components of a four vector is an invariant. The invariant corresponding to four velocity is 1. So what is the invariant for four momentum? With a simple derivation, we find that the invariant corresponding to the difference between the square of energy and the square of momentum is the square of mass. We need to carefully understand this formula because it's a fundamental equation in relativity. Firstly, in different literature, this formula might appear in slightly different forms, especially regarding momentum. Momentum can be expressed as a three-dimensional vector. Or more simply, we can denote the length of the three-dimensional momentum vector as p, resulting in a more concise formula. Secondly, this formula is derived in a unit system where the speed of light is set to 1. In this system, mass, energy, and momentum share the same units. If the speed of light is not set to 1, then the formula requires some adjustments. This formula also tells us that m is an invariant, meaning that when we observe the same particle in different inertial reference frames, we may find that the particle's energy and momentum vary across these frames, but its mass remains constant. Simply put, a particle has different energy and momentum at different speeds, but its mass stays the same. In physics textbooks from several decades ago, you might find a different description, where mass was described as increasing with velocity. The reasoning was that as velocity increases, more energy or momentum is needed for acceleration, implying greater inertia and hence greater mass. However, this idea has largely been abandoned in modern physics literature. You can think of the mass described in older texts as what we now refer to as energy, while what we describe as mass today corresponds to what was previously called rest mass. In our description, mass is an invariant, an intrinsic property of a particle, much like its charge or spin, and it does not change with the reference frame. This formula, which expresses the relationship between a particle's energy, momentum, and mass, also provides a clue to understand massless particles. This is what we will cover next. For photons, their mass is zero, and they travel at the speed of light. In this case, using velocity and mass to calculate the energy and momentum of a photon no longer works, because both the numerator and denominator in the formula would be zero. However, the relationship between energy, momentum, and mass still holds. When the mass is zero, we find that energy equals momentum. If the speed of light is not equal to 1, energy is momentum times the speed of light. In a plot of momentum versus energy, draw the curves representing the relationship for particles with different masses. The photon, which has zero mass, corresponds to a straight line. Many people mistakenly believe that a photon has no momentum. This misconception may stem from Newtonian mechanics, which suggests that an object with zero mass must have zero momentum. Additionally, because we feel the warmth of sunlight but not its push, this misunderstanding is further reinforced. But this understanding is incorrect. The momentum of a photon is its energy divided by the speed of light. The reason we don't feel a push from light isn't because photons have no momentum, but because their momentum is too small to be detected by human senses. In future interstellar travel, solar sail technology could offer a continuous way to propel spacecraft. This method uses the momentum of photons from stars to provide a gentle and steady push. Positronium decay is a simple but interesting physical phenomenon that clearly illustrates the principles of energy conservation, momentum conservation, and the relationship between energy and momentum for massless particles. There's a particle called positronium that consists of an electron and a positron orbiting each other. It's electrically neutral, and its mass is approximately the mass of 2 electrons. The positron is the antiparticle of the electron. If you let a positronium atom sit around for a while, these 2 antiparticles will annihilate each other, producing 2 photons. A massive positronium transforming into 2 massless photons makes no sense at all in pre-relativity physics. However, within the framework of relativity, this phenomenon can be fully understood. Let's start with the conservation of energy for the system. Positronium has a mass of m, and in relativity, a particle at rest has an energy equal to mc squared. Suppose the energies of the 2 photons are E1 and E2. Because total energy is conserved before and after the reaction, E1 plus E2 equals mc squared. According to the relationship between energy and momentum for massless particles, a photon's energy equals the magnitude of its momentum times the speed of light. Since positronium starts out at rest, the total momentum of the system is zero, meaning the total momentum of the 2 photons must also be zero. This implies that their momenta must be equal in magnitude but opposite in direction. In other words, the magnitudes of the momenta p1 and p2 are the same, both being p. From this, we can conclude that the momentum of each photon is equal to the mass of the positronium times the speed of light, divided by 2. This is the mechanism by which mass turns into energy. Of course, the mass was always energy, but in the frozen form of rest energy. When positronium decays, it produces 2 massless photons that carry energy. These photons may then interact with other matter, perhaps heating the atmosphere or being absorbed by electrons to generate a current, and so on. The thing that's conserved is the total energy, not the individual masses of particles. We can further use the de Broglie wavelength formula to calculate the wavelengths of the 2 photons produced by positronium decay. Of course, this goes beyond the realm of relativity and into quantum mechanics.